Hi there, welcome. This is a realistic DevOps interview simulation focused on rate limiting and abuse protection in production systems. I'm going to ask you behavioral and technical questions the way a real interviewer would. After each question, I'll provide a strong sample answer so you can compare your thinking with what a solid candidate might say. Before you listen to the answers, pause the video and respond out loud as if you were in the interview. Treat this seriously. That's how you actually improve. If you find this helpful, subscribe so you don't miss the next deep dive. Let's begin. Warm-up behavioral questions. First question. Tell me about a time when a production system was under unexpected load. What did you do? Pause and answer. A strong candidate might say, in one case, we had a marketing campaign go live without proper coordination. Traffic spiked about 5 times higher than our normal peak within minutes. The system didn't immediately crash, but latency increased and error rates started creeping up. My first priority was to stabilize. I checked dashboards for CPU, memory, request rates, and database connections to understand where the bottleneck was. We saw that the application tier was saturating CPU and our database was hitting connection limits. Short-term, we scaled out the application layer and increased database connection pool settings carefully while monitoring impact. We also enabled a temporary rate limit on certain non-critical endpoints to reduce background traffic. After stabilization, we ran a post-mortem. The main issue was lack of traffic forecasting and no protective throttling in front of the most expensive endpoints. We implemented rate limiting at the API gateway and added load testing scenarios to simulate campaign traffic before future launches. The key lesson for me was that scaling alone is not enough. You need protective controls that prevent a single event from overwhelming shared resources. Second question, describe a situation where you had to push back on a product or business team for reliability or security reasons. Pause and answer. A strong answer might sound like this. We once had a feature that allowed unauthenticated access to a public endpoint intended for analytics. The product team wanted no friction for users. From an engineering perspective, the risk was abuse, scraping, and potential denial of service. Instead of just saying no, I framed it in terms of business impact. I explained that open access without limits could increase infrastructure costs unpredictably and even affect availability for real users. I proposed a compromise. We kept the endpoint public, but we introduced IP-based rate limiting and anomaly detection. We also set usage caps and monitoring alerts. This way, the product goals were met while reducing abuse risk. I've learned that pushing back works best when you translate technical risk into business language and propose a concrete alternative. Third question. How do you approach designing for reliability when you know you cannot prevent all bad actors? Pause and answer. A strong candidate might say, I assume that abuse will happen, so instead of focusing only on prevention, I design for containment and resilience. That means layered controls, authentication and authorization where possible, rate limiting and quotas at the edge, circuit breakers and timeouts internally, isolation between critical and non-critical services so abuse in one area does not cascade. I also focus on observability. You cannot defend what you cannot see. So I want visibility into request patterns, spikes, geographic anomalies, and per-client usage. Reliability under abuse is less about perfect protection and more about limiting blast radius and recovering quickly. Now let's move into deeper technical questions. First technical question. Explain rate limiting to me. What is it and why is it necessary? Pause and answer. A strong answer might sound like this. Rate limiting is a control mechanism that restricts how many requests a client can make within a defined time window. It protects systems from abuse, accidental overload, and unfair resource consumption. From a reliability perspective, it ensures that one client or one class of traffic cannot monopolize CPU, memory, database connections, or downstream dependencies. From a security perspective, it reduces the impact of brute force attacks, scraping, credential stuffing, and denial of service attempts. I usually think of rate limiting as part of capacity management. Every system has finite resources. Rate limiting enforces fairness and preserves headroom for legitimate traffic. Second technical question: what are common rate limiting algorithms, and how do you choose between them? Pause and answer. A strong candidate might respond, there are several common algorithms. The fixed window counter counts requests within a static time window, like 100 requests per minute. It's simple, but can allow burstiness at window boundaries. The sliding window approach smooths that by calculating usage over a rolling time period. It's more accurate but slightly more complex. The token bucket algorithm allows bursts up to a certain limit while enforcing a steady refill rate. It's flexible and often used in API gateways. The leaky bucket enforces a constant outflow rate, which is useful when you want to smooth traffic strictly. When choosing, I consider user experience and system capacity. If short bursts are acceptable and resources can handle them, token bucket works well. If strict smoothing is needed to protect a fragile downstream system, a leaky bucket might be more appropriate. I also consider implementation constraints. If I'm using a managed API gateway or CDN, I leverage their built-in capabilities rather than reinventing it at the application layer. Third technical question: where in the architecture should rate limiting be implemented? Pause and answer. A strong answer might sound like this. Ideally, rate limiting should happen as close to the edge as possible. That means CDN, load balancer, API gateway, or WAF level. If you stop abusive traffic at the edge, you prevent unnecessary load on internal services, application servers, and databases. However, I don't rely on just one layer. For critical services, I might implement additional limits at the application layer, especially if the limits depend on user identity or business rules that the edge cannot see. In distributed systems, I also consider per-service protection. For example, a back-end service might enforce its own request concurrency limits or circuit breakers to prevent cascading failures. Defense in depth is important. Edge rate limiting protects globally, while internal controls protect locally. Fourth technical question: suppose your API starts returning 429 errors during peak traffic. How would you determine whether that is healthy protection or misconfiguration? Pause and answer. A strong candidate might say, first, I would correlate the 429 response rate with traffic metrics. If request rates exceed the configured limits consistently and the system remains stable with acceptable latency and error rates otherwise, that could indicate the rate limiting is doing its job. Next, I would check who is being limited. Are the 429s concentrated on a few IPs or API keys, or are legitimate users broadly affected? If legitimate users are being throttled during normal expected traffic, that suggests misconfigured thresholds or inaccurate capacity planning. I would also examine business metrics. Are conversions dropping? Are customer complaints rising? A technically correct rate limit can still be wrong from a business standpoint. Finally, I would compare current load against historical baselines and load test results. If traffic growth has outpaced limits, the system may need reconfiguration or scaling rather than tighter restrictions. The key is to treat rate limiting not as a static rule but as a dynamic control aligned with real usage patterns and system capacity. Next question. You have a multi-region architecture behind a global load balancer. How would you implement rate limiting in a distributed system without causing inconsistencies? Pause and answer. A strong candidate might say, in a distributed system, the challenge is that traffic can hit multiple regions or instances, so naive per-instance counters can allow a client to exceed global limits by spreading requests across nodes. First, I would clarify the requirement. Do we need strict global limits per user, or are approximate limits acceptable? Strict global consistency increases complexity and latency. If strict global enforcement is required, I would use a centralized or globally replicated data store, such as Redis, with clustering or a managed service that supports atomic increments across regions. The rate-limiting logic would rely on atomic operations like INCR with TTL to maintain accuracy. However, that introduces cross-region latency and potential availability trade-offs. If the central store is unavailable, rate limiting might fail open or fail closed. I would define that behavior explicitly. If approximate limits are acceptable, I might implement region-level rate limiting and divide the global quota across regions. For example, if a client is allowed 1,000 requests per minute and we have 2 active regions, each region enforces 500. This reduces cross-region coordination but risks uneven traffic distribution. In practice, I often combine both: edge-level rate limiting at the CDN for course protection and application-level per-user limits in a distributed cache. The key is understanding whether precision or availability matters more for that use case. Next question. How would you protect an authentication endpoint from credential stuffing attacks without harming legitimate users? Pause and answer. A strong candidate might respond, authentication endpoints are sensitive because they are both security-critical and user-facing. First, I would implement IP-based and user-based rate limits. For example, limit the number of login attempts per IP and per account within a short time window. Second, I would add progressive backoff. After several failed attempts, introduce increasing delays or temporary account lockouts. That reduces the effectiveness of automated attacks. Third, I would integrate bot detection mechanisms, such as CAPTCHA or behavior-based anomaly detection, especially after suspicious patterns. However, there are trade-offs. Strict IP limits can hurt users behind NAT, such as corporate networks or mobile carriers. So I would monitor false positives carefully. I would also ensure that error messages do not leak whether a username exists. Rate limiting should apply consistently to prevent user enumeration. Finally, I would add observability around failed login patterns, geographic distribution, and spikes. Protection is not just about blocking requests, but also about detecting evolving attack patterns and adjusting thresholds accordingly. Next question. Suppose a critical downstream service cannot handle more than 200 requests per second, but your front end can receive thousands. How would you design to prevent cascading failure? Pause and answer. A strong candidate might say, first, I would treat the downstream service as a protected dependency. Its capacity defines the upper bound for safe traffic. At the edge or API gateway, I would enforce a global rate limit that ensures aggregate traffic does not exceed the safe threshold for that dependency. Inside the application, I would implement a circuit breaker pattern. If the downstream service starts timing out or returning errors, the circuit breaker opens and stops sending requests temporarily. That prevents threads from piling up and exhausting resources. I would also use request queues with bounded capacity. If the queue fills up, we reject or shed load gracefully, rather than allowing uncontrolled backlog growth. Additionally, I would consider caching responses if applicable, especially for read-heavy operations. That reduces direct dependency on the fragile service. The trade-off is between availability and strict correctness. In some cases, returning a degraded response or partial data is better than letting the entire system collapse. Next question. How do you differentiate between a traffic spike from success and a distributed denial of service attack? Pause and answer. A strong answer might sound like this. The first step is to analyze traffic patterns. Organic spikes from success usually correlate with business events, marketing campaigns, product launches, or known time-based patterns. They also tend to have realistic user behavior characteristics, such as authenticated sessions, normal request sequences, and diverse but plausible geographies. DDoS traffic often shows anomalies: extremely high request rates from limited IP ranges, malformed requests, repetitive patterns, or unusual user agents. I would compare current traffic against historical baselines. If the spike is aligned with known events and the traffic looks consistent with normal user journeys, it is more likely legitimate. However, the distinction is not always clear. So I design the system to withstand both. Rate limiting, auto-scaling, and WAF rules should handle unexpected spikes regardless of origin. Importantly, I would avoid blocking aggressively without evidence. Overreacting can harm real users. I prefer layered defenses and gradual mitigation, tightening controls as confidence in malicious behavior increases. Final question for this section. Imagine your rate-limiting rules are too strict and are blocking a high-value customer's automated integration. How would you handle it? Pause and answer. A strong candidate might say, first, I would validate the claim by examining logs and metrics. Are their requests being throttled? At what rate? Is their usage exceeding documented limits? Next, I would review whether their usage pattern is aligned with our published API contract. If they are operating within reasonable expectations, but our limits are outdated, that is on us. I would avoid making ad hoc exceptions without structure. Instead, I would consider implementing tiered rate limits. For example, standard limits for general users and higher quotas for premium or partner clients. I would also evaluate whether their traffic pattern introduces risk to system stability. If granting higher limits to them threatens other users, we may need to scale capacity first. Communication is key. I would explain the rationale for limits and propose a sustainable solution, such as dedicated API keys with higher quotas, scheduled batch windows, or architectural changes like webhooks instead of polling. Rate limiting is both a technical and business control. Adjusting it requires balancing fairness, revenue, reliability, and long-term system health. Pressure and judgment. Questions. Let's move into the harder part of this conversation. These are not clean textbook problems. These are judgment calls. First question. It is 2 a.m. You are on call. Your monitoring shows that your rate-limiting rules are blocking 30% of incoming traffic. Revenue is dropping. Marketing says a campaign just went live and traffic is higher than expected. Security says the spike looks suspicious. You do not have full clarity yet. What do you do? Pause and think it through. A strong candidate might say, at 2 a.m., I focus on stabilizing the system first. The immediate risk is revenue loss and customer impact. But blindly removing rate limits could expose us to an attack, so I would start by segmenting the traffic. Are we seeing normal user behavior patterns or clear anomalies, such as repeated identical payloads or concentrated IP ranges? If the data suggests legitimate growth, I might temporarily raise rate limits in a controlled way, not remove them entirely. For example, increase thresholds incrementally while monitoring backend saturation metrics like CPU, latency, and error rates. At the same time, I would involve security early, even if asynchronously. Share samples of traffic patterns and ask for quick validation. The key is not to make a binary decision. It is about controlled adjustment under observation. Raise limits slightly, monitor. If system health degrades, roll back quickly. Under uncertainty, I optimize for reversible decisions. Small, measurable changes. Protect the system while buying time for clearer data. Next question. Your API is being abused by a third party who is technically staying within documented rate limits, but is causing significant load due to inefficient usage patterns. Do you change the rate limits, block them, or redesign the system? Pause. A strong answer might sound like this. First, I would confirm the impact. Are they causing performance degradation for others, or just increasing infrastructure cost? If system stability is at risk, I would implement more granular rate limits. For example, per endpoint or per operation limits rather than global per user limits. If they are staying within published limits, blocking them without discussion could damage trust. So I would reach out, clarify usage patterns, and propose alternatives such as bulk endpoints or webhooks instead of aggressive polling. At the same time, I would examine whether our API design unintentionally encourages inefficient behavior. Sometimes abuse is really just poor API ergonomics. The mature response balances enforcement with collaboration. Rate limiting is not just punishment, it is about shaping safe usage patterns. Next question. Suppose a regulator requires you to guarantee fair access to all users. However, your largest customer accounts for 40% of traffic. If you strictly enforce equal rate limits, you risk losing that customer. If you prioritize them, smaller users may suffer. How do you decide? Pause. A strong candidate might respond, This is a business and ethical trade-off, not just technical. I would first clarify what fair access means in the regulatory context. Does it require equal limits or non-discriminatory policies? If equal limits are mandated, then compliance takes priority. Legal and regulatory risk can outweigh short-term revenue. However, fairness does not necessarily mean identical quotas. It can mean transparent, published tiers that apply consistently to all customers. I would propose a tiered model where larger customers pay for higher guaranteed capacity, but system protections ensure they cannot starve smaller users. Technically, that might involve resource partitioning or weighted rate limiting. Each tenant has reserved capacity plus burst capacity within defined bounds. The decision is not about choosing one side blindly. It is about designing a policy that aligns with compliance, business sustainability, and system reliability. Final pressure question. Your team proposes disabling rate limits entirely during peak events because auto-scaling can handle the load. It simplifies logic and reduces false positives. Do you agree? Pause. A strong candidate might say, I would challenge that assumption. Auto-scaling handles resource scaling, but it does not protect against unbounded usage or logical abuse. If a client sends requests that are computationally expensive or trigger downstream bottlenecks, scaling compute alone may not prevent cascading failures. I would ask for evidence. Have we load tested with rate limits disabled? Do we understand the true capacity ceiling of every dependency, including databases and third-party services? If we disable rate limits, we are effectively trusting that every client behaves responsibly. That is rarely a safe assumption on the internet. However, I am open to reducing strictness during predictable high-demand events if supported by testing and monitoring. The mature position is not rigid. It is risk-aware. Rate limits are guardrails. Removing guardrails requires strong proof that the road ahead is safe. Take a moment and reflect on the questions we covered today. Rate limiting is often treated as a simple throttle, but as you have seen, it sits at the intersection of security, fairness, business incentives, and system stability. Which question felt the hardest for you? Was it the 2 a.m. decision under incomplete information? Was it the tension between a large customer and fairness to everyone else? Or was it deciding whether to trust auto-scaling instead of protective limits? These are not questions with perfect answers. They are questions that reveal how you think under uncertainty. If you are preparing for senior DevOps, SRE, or platform roles, practice articulating your reasoning out loud. Not just what you would do, but why. Interviewers are listening for judgment, trade-offs, and risk awareness. Pause the video. Re-answer the toughest question in your own words. See if you can explain your reasoning clearly and calmly. If you found this simulation useful, subscribe and continue with the next interview scenario. Each session is designed to sharpen your thinking, not just your technical vocabulary. The goal is not to memorize answers. It is to develop decision-making instincts that hold up when the pressure is real. I will see you in the next one.